In this section, we're going to look at a particular type of system. Remember that a system is a way to transform one signal into another. A system could be an electrical circuit, that would be a linear circuit that transforms, say, an input voltage into an output voltage or a current going through a particular branch. A system might also be an electronic circuit, say a nonlinear system with amplifiers or diodes or transistors. A system more generally can be thought of as a mathematical equation that relates inputs to outputs. What we're going to do in this section is we're going to talk about a particular type of system, a system that has two properties, linearity and time invariance. And we're going to look at why we study these systems. The first reason that we're interested in studying these systems are that they are sufficient and very powerful for modeling many real physical systems, including electrical and mechanical systems that have linear components such as resistors, inductors, and capacitors, but not diodes or transistors, and also any system that can be described with a linear constant coefficient differential equation that is homogeneous. Also, we will show later in this chapter that if you model what happens to the system when the input is a simple delta function, that the output that you measure fully describes what the system does. So this gives us a very powerful model for having one theoretical test function that fully describes a system. Now, in the real world, we can't have deltas, but we can approximate them by signals that rise to their maximum for a very short amount of time and then turn off. And that will be useful later as we approach digital signal processing and look at analog to digital and digital to analog conversion. Now, a result of this that we will get to later in this chapter is this output that you measure when you give an input as simply the delta or the Dirac's delta or impulse function. That output that you measure, that response to the impulse input, can be used in a method called convolution to efficiently calculate the output for any possible input the circuit might have. So this is going to be a method of calculation that's also going to lead to very efficient digital applications and very powerful and efficient methods of analyzing these systems. Another property of linear systems that you know from circuits is that they can change the amplitude and phase of an input signal going to any output signal, but they cannot change the frequency. They cannot introduce frequencies that are not there. As you know from your circuits classes, and some of you will be learning later or have already learned in electronics classes, systems that change the frequency of an input or an output, such as doubling it or tripling it or otherwise modifying it, are nonlinear. They have components such as diodes and transistors, which do not obey linear constant coefficient difference equations. Finally, the tools that we use for analyzing these linear time invariant systems result not only in a simple analysis, but they result in processes that we can reverse to say that we want to have a system with a certain type of behavior, and then we can reverse the analysis process and arrive at a design process to develop and implement that system with that given behavior, whether it be through a linear electrical circuit or a digital signal processing implementation. We'll see examples of these later in this course and the digital applications in the next course. So there are some key properties that we need to look at as we approach linear time invariant systems. Ultimately, we're going to be talking about linear time invariant or LTI systems. This consists of two parts: the fact that a system is or is not linear, so we're going to take a careful look at what that means. To relate this to circuits, a system is linear if it obeys superposition. So superposition, as you may remember, means that I can treat inputs separately and analyze what the system does to them, and then add to the results together to get the overall result of the system. Also, the other property is time invariance. We will learn exactly what that is mathematically and how to test a system and determine whether it has the time invariant property. A property of being linear has two properties that build to make it. And they are whether the system is scalable and whether the system is additive. So we're going to look at what each of these properties means, how we can test a system to see whether it has them, and then we'll do some more detailed analysis examples. A system is scalable if it has this property. Here we have a system T receiving an input X as a function of time, and it produces an output as a function of time. Now, we say that system is scalable if I multiply the input by some constant, if that means the output will be what the output was originally multiplied by the constant. So if I know what X is and I scale X up, say by times 5 to make it a stronger signal but with otherwise the same shape occurring at the same time, if the system is scalable, then my output will also be scaled up times 5. So a lot of good systems that we might want to work with will have this property. For example, if I say y of t equals 3x of t, then I'm just multiplying the signal by 3, and if I start with something that's 5 times bigger, I'll get something that's 5 times bigger. If I do this, this is still a scalable system. This one is saying the output is equal not only to 3 times the input right now, but 2 times what the input was 1 second ago. And if I scale up the input by a factor, it will still be just a multiple of that. Let's go ahead and prove that. Let's replace x of t with a times x of t. So this is, we're going to change the input. And we're going to call this modified function, let's call it x star of t. So that's the modified x of t. Now, let's use this definition here of the system to see what happens when I change the input to x star of t. Let's call the corresponding output y star of t for this different input. And now we follow the system rule. The system rule here says that we follow our original equation for y of t. It says you take 3 times your input signal, and so I could write 3x star of t here, but let me just expand this out in terms of the definition of x star of t. And then it says you take twice the input x at t minus 1. So that could be twice x star at t minus 1, or I can replace x star with its definition, which is a times the signal, and this is at t minus 1. So now I have that. I can collect a common term here. I'll factor out the a. And now I realize that the value inside the outer parenthesis, 3x of t plus 2x of t minus 1, that exactly matches the original definition of the system. So I can replace that with the original output, and so I arrive at this. And that is just the definition. The new output, y star of t, is exactly following and equal to the scaled up version of y of t. Now, let's do an example of a simple system that does not obey scaling. Let's do this system. Let's start a new slide. Okay, so this system will be y of t equals 3x t minus 2. Okay, we already know that systems like that obey scaling. And let's just make a very simple change. Let's say plus 5 volts. Okay, so now we want to see, does this system, let's call the system t, does the system obey scaling? So what we do here is we have a copy of the system t. We're going to input x and get y out. And then we're also going to say if I input a times x, I'm going to get out some other signal. So we'll call the input x star, which is a times x. I get some other output, which is y star, and I ask, does that equal a times y? And these are all functions of time. I'm just not writing the time variable. So when we test for scaling, this is what we do. So I will say x star again is going to be a times x. And now I want to know what the output y star is when the input is x star. So it's going to be following the rule 3 x star of t minus 2 plus 5. Now I substitute in the definition of the scaled version. X star is the scaled version of x. So I have 3ax, and it's delayed by 2, plus 5. And now I try the trick that I tried before, which is I try factoring out a of the whole expression, and I get 3x t minus 2 plus, I want 5, but I have to factor out an a, so I can't quite get what I want there. This term right here, coming from the 5, coming from something that does not have x itself, or a linear transformation of x, such as x delayed by 2 samples, next to it, caused me to get this non-homogeneous term, and it caused me to end up with a non-scalable system. So one simple way of saying it would be, if you double the input to a system and its output doesn't double, you immediately have proof that the system is not scalable. Okay, let's go on and take a look at the additivity property. So here I have two functions, x1 and x2 of t, and I add them together, and that gives me my overall input x of t. And then that is going to be the input to our system. Now, if the system is additive, then I can borrow a trick from superposition, and I can say, for analysis purposes, let me pretend that there are two independent copies of the system, and let me separately consider the parts of the input, x1 and x2, and let me find what the outputs are to each of those, and then let's add those together and get the output y. Systems that obey the additive property follow this rule, and if the system is additive, then the fact that I considered the system separately and then for each part of the input and then added the results together will give me the same result as if I did this in the opposite order. It will give me the same result as if I first added the signals together. So I have x of t, which equals x1 of t plus x2 of t, and then I ran that into one copy of the system t, and I'm going to get another output. Now I'm going to call this y star of t, because I have a different path to get y above, so I don't want to give it the same name. And if y star is equal to y, then the system has the additive property. If those two signals are not equal, then that system T is not additive. So here, the reason we're interested in doing this are the same reasons that you're interested in knowing whether a system obeys superposition. For analysis purposes, if I have a signal X and I break it down into two simple parts, maybe this is a cosine at 50 hertz and this is a sine at 75 hertz. I would like to be able to analyze the effect on each of those separately. Maybe this is a sinusoid, maybe this is a step function, and the overall signal is the sum of the two. I would like to analyze them separately. Now, when I actually implement the system, I don't want two copies of the hardware. I want there to be one copy of the hardware. If the system obeys superposition and has this additivity property, then the analysis result I get, considering the output to each of the stimuli separately and then adding the outputs together, will be the same as if I added the signals together and then found the output. Let me give you an example of a system that is not additive, and we will prove that it is not additive. Y of t is equal to the value of x at t squared. So now if we trace this through, that is, we have a rule for calculating the input from the output. So we have x is equal to x1 plus x2. So we have x1 and x2, two potential parts of our signal, and we run them through. So we're going to get x1 squared of t. We're going to get x2 squared of t, and then we're going to add those two together. So our y of t is going to be x1 of t squared plus x2 of t squared. So that is the analysis assuming superposition holds. Now let's find out what the system actually does to the sum of two signals. So y star of t is going to be x star squared of t. And if I write that out a little more literally, you take the function x star of t and you square it. So the function x star of t is going to be the sum of is going to be the same as x of t here. It's x star of t equals x of t. It's going to be the sum of the two inputs, x1 of t plus x2 of t, and then we square that. And now I do first inner, outer, last. So we have x1 of t quantity squared. I have the cross terms. I have x1 times x2 and x2 times x1. Multiplying two functions is commutative, so I get 2 of x1 of t, that function, times x2 of t. And finally, I have the last term, x2 of t quantity squared. This differs from the separately considered inputs because it has this cross term. Therefore, this is non-additive. So I have a system that does not meet the additivity property. So as a quick review of where we're going regarding scaling and additivity. Scaling is a property you can test for. We did on the last slide. Additivity is another property, and if the system has both of these properties, then we say it is a linear system and it obeys superposition. For most well-behaved systems that we're going to see, scaling and additivity go together, but formally we do need to check that it has both of the properties to declare that it is a linear system. We have one more property to consider on our way to linear time invariant systems, and that is time invariance. A time invariant system means if I delay the input, then I will delay the output by the same amount, but I will not otherwise change the output. We can do a block diagram view of what this system property means, similar to what we did for scaling and additivity. If I have a system T and I give it an input signal X and it processes that, it'll give me, of course, an output signal that we usually call Y. Now, if I then take that signal and I delay it, I don't want to use capital T to mean two different things here. If I delay it by tau seconds, then I get another input which we'll call Y star. And if that Y star is equal to the original output delayed by the same time delay tau, then we say it is a time invariant system. So a time invariant system is one that acts the same 1 second from now and 1 hour from now as it acts now. If I give it an input and measure the output now, and I do the same thing 1 second from now or tomorrow, it will give me the same output. If the system does not have that property, then we would say it is not a time invariant system. So let's give an example. Let's say our output is equal to twice the input plus 5 times time. This would be an example of a system that is not time invariant because I have this ramp of time being added to all signals. So if I delay the input X by so many seconds, this ramp is going to have grown larger. So one clue, this is not the only clue, but one very good clue that you are dealing with a system that is not time invariant is a T here that is not used as a simple index or argument to your input function. So let's now use this block diagram on the right to show that this system is not time invariant. So our output Y of t here is going to be 2x of t plus 5t. Now, if I delay by tau, then we want to figure out, well, what is the input? So I have a new input, let's call it x star of t, which is going to be x of t delayed by tau seconds. So now we want to run that through the system, and we're going to call its output, just as we have over here in the diagram, y star of t. So we're going to calculate this y star of t. The block diagram says you get y star of t by applying the system to the input. So let's go ahead and do that. Y star of t says you apply the system. Here is the defining equation for the system. We're going to apply that to the input. So twice x of t, twice the input. So twice x star of t plus 5t. Now I substitute in what x star is. X star is the delayed version of x. So it's x of t minus tau plus 5t. Now, I want to be able to see if I can express the right-hand side as a time-delayed version of the original output y of t, which I have written right over here. So the x of t part, I already have delayed by tau, but in order to write in this time-delayed version, I would also want to have a copy of this 5t term delayed by tau. So the delayed version of that, would be 5t minus tau. But in order to make this equal, I have to make the equation balance out. So since I'm subtracting a 5 tau, I'd have to add a 5 tau. But now what I have is this expression right here is just the original output delayed by tau. So this expression here is y of t delayed by tau, but unfortunately I have this extra 5 tau hanging on the end here. So if I look at this, my y star, I'm asking, is it equal to the delayed version of the original output? Well, it kind of is, but it has this extra factor that is not a delayed version. In fact, it's dependent on what the delay is. So this would be an example of a system that is not time invariant. So that is it for this video. I'm going to add one more video on this section that goes through a couple more examples of systems that are or are not linear and are or are not time invariant.